All right. Hi, everyone. Welcome to another online causal inference seminar. Today, we have plenty of people here. We actually have a talk by Robin Evans from University of Oxford on parametrizing and simulating from causal models. In the Q&A to help Robin answer questions, we have Daniel Manella from Oxford and Vanessa Didelez from BIPS. So if you have questions, please ask them as during the talk. They will be there to help answer questions, to help Robin answer questions as well. After Robin's talk, we have a discussion. Our discussant today is Larry Wasserman from CMU, so we very much look forward to that part of the talk today as well. And now I will hand it over to Georgia, who handles the Q&A today.
Thanks, Emma. Okay, so as always, please submit your questions if you have them as they come up in your mind through the Q&A. There should be a button at the bottom of your screen with Q&A. Please refrain from using the chat since it makes it easier for us to keep track of the questions. Like Emma said, we have Daniel and Vanessa in Q&A answering the questions, and maybe if you're lucky, your question will be asked live as well. So I think we're ready for Robin now.
Great.
Feel free to share your screen.
Right. I think everyone can see that.
Yes.
Okay. Well, thanks very much, Georgia and Emma and Ying, for inviting me to give this talk. It's a great privilege. So, I mean, in this series, which has now been going on for 3 years, the 3rd anniversary on Friday, there have been lots of talks all about different kinds of causal models. And today I'm going to talk about something maybe slightly different, which is how for some of these causal models, you might parameterize them. And that can give you a likelihood, which enables you to simulate from them and also to fit them using likelihood-based methods. So all of this is joint work with Vanessa Didelez, who, as Emma said, is from the University of Bremen and the Leibniz Institute for Prevention Research and Epidemiology, known as BIPS. And as sort of outlined for my talk today, I'm going to start off by giving a very brief introduction to causal inference and some problems which exist with some causal models as they are generally used. Then we're going to give, in this next section, our solution, which involves using marginal modeling techniques from marginal modeling. In the 3rd part, we'll have some more theoretical results. In the 4th part, some simulations, and then we'll end with some other applications of our parameterization. Okay, so section 1, what is causal inference? So a kind of typical problem in causal inference is where we want to model an outcome as though the treatments that have been assigned had been assigned in a specific way. And obviously, the most common way we might want to imagine that the treatment was assigned is at random. Unfortunately, observationally, this is not often the case. So at most, we might be willing to assume that there's some set of observable covariates that we've measured that they can be used to identify the causal effect because they are considered to be sufficient to control for confounding. So this basically means that any statistical estimator of the causal estimand of interest, which in our case here is the causal effect of when we intervene on A, what happens to the distribution of Y, is going to involve either some adjustment using these covariates Z or some reweighting. So we might first estimate the distribution of A given Z and use the propensity score to reweight, or some other fairly complicated method for identifying this causal effect. And a sort of consequence of this is that the interventional likelihood for such a model in terms of the observational data that you get from it is very complicated. And it means that basically you can't do likelihood-based inference. So for example, you can't find the maximum likelihood estimator of the strength of this edge in the causal sense because you can't evaluate the likelihood. And it also precludes anything like a fully Bayesian approach to modeling something like this. Okay, so to take a slightly more concrete example, this is a causal model, and it represents a sequential treatment study. So here, the story is at the beginning of the study, a doctor randomizes her patients to have some dose of a treatment, and we're going to call that dose A. And then a little later, she evaluates some intermediate outcome, which we're going to call Z. And then on the basis of both that initial treatment and the first outcome, she then re-randomizes a second treatment B, conditionally on those first two values. And then finally, we observe this final outcome, Y. And then, of course, because these two observations are measured on the same patients, we'll assume that they'll be correlated due to unobserved characteristics of the patients. And we represent that by this latent variable U, which has Z and Y as its children. And then maybe we're interested in what would have happened if B had been assigned completely at random rather than dependent on the values of A and Z. So in fact, we want to sort of probabilistically sever these two edges. And it was first shown how to do this in a seminal 1986 paper by Jamie Robbins using what he calls the G formula. So what we do is take our factorization of the observable distribution, so A, Z, B, and Y, and factorize it according to the causal ordering. And then what we notice is that the thing we need to kind of get rid of, the dependence we need to get rid of, is B's dependence on A and Z. Unfortunately, that is one of the factors in this factorization. So all we need to do is delete that factor. And for A, it doesn't depend on anything. So all we need to do is delete its margin at the front here. And that leaves us with the distribution of Z given A multiplied by the distribution of Y given A, Z, and B. Okay, and that gives us the interventional distribution over both Z and Y jointly. And of course, it is just a probability distribution. So if we want to know the distribution over Y only, all we have to do is integrate this quantity over Z. And that gives us the G formula, which is in this green box down here. And this quantity is sometimes called a marginal structural model. And this sort of shows that you can identify it relatively straightforwardly. So that's great. There are some problems with it though. So suppose that you're interested in maybe testing whether or not A actually has a causal effect on Y conditionally on B. So in other words, does this marginal structural model actually depend upon A at all? And it turns out that's quite difficult. Why is it so difficult? Well, partly it's because the likelihood is so complicated. So in discussing marginal structural models, Robbins himself notes there's a great difficulty in performing likelihood-based inference because the likelihood for these kinds of models is what he calls a computational nightmare. So in other words, if you try and write down a likelihood which contains some particular nice parametric model for this piece of the distribution, this functional, then what you're left with is a bit of a mess. And then the second reason we have a problem is because this model suffers from something called the Genol paradox, which is due to Robbins as well, but also Larry, who's going to talk about this afterwards. So what you might think of doing is, well, we've got these two conditional distributions, so why don't we just specify a nice model for Z given A, and another nice model for Y given A, Z, and B, then compute what this quantity is, and then maybe we fiddle with the parameters of these two models a bit until we get to a point where the thing does not depend on A. Unfortunately, that doesn't work, as Jamie and Larry showed. So the idea is basically, unless your models are completely linear, in which case you don't really have any problems at all, you can't necessarily find a collection of parameter values which will give you this quantity not depending upon A at all. So let's take a very simple example. Let's suppose that Z is binary and we model it as a logistic regression conditional on A, and that Y is unbounded and we model it as mean as a linear function of A, Z, and B. So it's pretty easy to then compute that the interventional mean of Y after we go in and fix A and B to particular values is given by just these two terms which come out, and then this final term, the Z, will just become the mean of Z given A, right, which is x bit of alpha A. So we can see now that this null hypothesis will only hold if, first of all, beta A is 0, because we need this term to be 0. And second of all, if this final term is constant in capital A. So that means either beta Z has to be 0, or alpha has to be 0. So we need, and if we translate this into independences, this means that either y is completely independent of a and z given b, or essentially a is independent of z and of y given z and b. So we need an extra independence above the one that we're actually interested in, which is we want y not to be independent of a given b in this causal sense. So this is a much more restrictive hypothesis that we actually end up having to test if we use these parametric models. So the sort of lesson here is that just specifying nice parametric models for these two distributions and then playing around with the parameters is not the way to go if you want to simulate from a model where this quantity does not depend upon capital A. And Larry and Jamie also show that if you have a hypothesis test of this model, and then you try to test it, assuming that these conditions are not true, then you will end up rejecting with probability 1 tending to 1 as the sample size grows. So another approach that people take generally when they're interested in doing inference is to propose models that are sort of over-parameterized, and therefore generally they're not congenial. So what do I mean by that? Well, a congenial model is one where for any combination of the parameter values, there is a distribution which represents the restrictions that you've imposed, whereas an uncongenial one tends to give too many restrictions, and there may not exist a distribution that satisfies them all. So here's a simple example from a paper by Loys et al. So they consider a mediation model with a treatment A, mediator M, and a binary outcome Y. And they suggest the following moment restrictions. So the first is that Y conditional on A is a logistic regression, so it's linear in A. And also that Y conditional on A and M is a logistic regression, so it's linear in A and M. But unfortunately, the logistic function is not collapsible, which means that unless beta M is equal to 0, and then the two models just collapse to be the same, then there is no non-trivial model that will satisfy these restrictions. So this is a sort of warning that if you try and just specify models and hope, then it's quite likely you will end up with a situation where there's no logical possibility of such a distribution existing. And I should just say, this works very well if you're interested in inference, and that paper is interested in inference and they get good results. And just in case you thought this was only a feature of static models, actually it's not. So there's the example of what are called history-adjusted marginal structural models, which show that the same thing can easily happen in a time-varying situation. So what is it that we want from this talk? The first thing is we'd like to be able to describe a joint distribution over the observational data of all the variables, so that's confounders, treatments, and any outcomes, that satisfies three properties. So first, we've got an explicitly provided parameterization of the causal function that we're interested in. So that's the P of y given do A and B in the previous example. We want to allow the rest of the distribution to be as flexible as possible. And we want it to remain coherent and unambiguous. So coherent, I mean, we don't want restrictions that aren't feasible to meet. And unambiguous, we want to say that we're specifying everything in the model. And next, we'd like to be able to simulate from that distribution P, such that, first of all, the data can exhibit a complex confounding structure if we're looking at it observationally. But if we perform the intervention, assuming it's identifiable, then we'll see that it does indeed obey the causal model that we specified back here in part 1. And then thirdly, we'd like to be able to fit these models, especially models that are typically only fitted in a semi-parametric way, such as marginal structural models, using likelihood-based methods. And because you may not want to do this because you might be worried about model misspecification, but it's useful from the perspective of seeing that the maximum likelihood estimator is the most efficient possible model, and therefore maybe using it as something like a lower bound for how good your inference could possibly be. Okay, so what is our solution to these problems? So what we're going to do is just rewrite the model a little bit to show that it is a bit more general. So I'm going to call this causal distribution I was talking about earlier, P star of Z and Y given A and B now, but I'm defining it in the same way. So we can ask what we know about this model. So we know the margin over Y because that's something that we've been given. So the analyst presumably wants to know what the parameters are in this piece. We also know something else about the other margin, so which is that it doesn't depend upon B. Right, so if we marginalize out Y here, we're just left with the ordinary distribution of Z given A. And that's because when we did the intervention here, we severed the dependence of B on Z given A. And so therefore, there's also no dependence of Z on B given A. So this is an important restriction that we have to impose on our model. Obviously, this isn't quite enough to specify the full conditional distribution here. So we need something else. And anyone who knows anything about marginal modeling will say you need some sort of conditional dependence measure for Y and Z under this distribution P star. And we don't sort of prescribe what this dependence measure has to be. In principle, it can be any model, any quantity which enables you to recover the joint distribution in a smooth way. But for every example in this presentation, I'm going to use a copula. And if they're both, if Z and Y are both discrete, you can use a conditional odds ratio. So the solution to this problem is to specify nice parametric models for 3 bits. The first is the distribution of what I call the past, which is everything before the outcome you're interested in. Then you have a model for the quantity of interest, which again, in our case was P of Y given do A and B. And finally, we have a parameterization for this dependence measure, which could be a copula or a conditional odds ratio or something else like a risk ratio. So these quantities have 3 great properties. So first of all, you can completely specify the joint distribution with these 3 things. So any distribution can be written more or less in this form. The first 2 things are always variation independent, which means any value of this distribution and any value of this distribution can combine to give a distribution that has both of them as part of it. But you can often also choose this third piece be variation independent. So for example, a copula and a conditional odds ratio are both always variation independent of their margins. And that obviously has big advantages. So for example, if you want to do Bayesian inference, you can just specify independent priors and not worry about whether that's coherent. And they also don't have any redundancy. So I'm not trying to specify anything in 2 different ways when I use this decomposition of the distribution. So because of this, we refer to it as a frugal parameterization. It gives us exactly what we want, i.e. the quantity of interest is parameterized, and then the rest of the model is specified only as much as it needs to be. Okay, so we've seen that there's sort of generally a tension between 3 different things. One is a simple specification of the joint distribution P, which obviously helps with things like simulation and likelihood-based inference, because computationally it'll just make it much easier to perform those 2 tasks. Then there's simple specification of the target of inference, which is this star distribution of the outcome given the 2 treatments, in order that the model is nicely interpretable. And then the third tension is with these marginal constraints, right? So I need to be able to enforce that Z is independent of B given A in the previous example. And in general, I need to make sure I can enforce constraints of that kind. And the frugal parameterization is sort of perfect for these second and third points. It gives you exactly what we want for the target of inference, and it can exactly enforce the constraints. And it sacrifices only a little bit for the nice, simple specification of the joint distribution, but it's not sufficient to prevent us from simulating from it or from doing likelihood-based inference. Okay, I'll just stop there and see if anyone has any questions.
Hi, We don't have any questions for the moment, so we can continue with the talk. Generally, when you stop and ask questions, people remember to ask their questions at that moment. So maybe in 2 minutes we'll have one. But
Okay.
You can go ahead for now.
Okay, thanks very much. So to generalize what we've already seen, I'm going to use the following notation. So A is going to be, in general, a vector of the treatments and possibly effect modifiers. So anything I want to be in my conditioning set. Y is going to be a vector of all the outcomes that we're interested in. And Z is going to be a vector of any variables that we want to be marginalized. So a sort of cartoon of the setup is that you have these observed confounders Z and then a treatment A and an outcome Y. But actually, as we'll see, it doesn't have to be as simple as that. We've already seen that you don't have to have all the treatments be after the covariates. So in this model, we had a treatment that came before the covariates. And in fact, there's no strict causal order on any of these quantities. And the fact that they can be vector valued also makes this a lot more flexible than it might initially seem. And then the object that we're interested in is some conditional distribution that we obtain on the outcomes given the treatments and effect modifiers. So this is a marginal distribution. But the margin, of course, is not the standard margin. So we need some way of describing which margins are allowed. So we come up with this notion of what we call cognate probability distributions. So we're going to define a kernel function W. So this is just some conditional distribution over the covariates conditional on the treatments. So it's a conditional distribution, so it has to be non-negative and it has to integrate to 1 over the values of the covariates for each value of the treatment. And we can allow it to be a smooth function of the past. So it could be, for example, the margin over Z, or it could be the conditional of Z given A, as we'll see in a minute. And then we're going to say that a probability distribution P star of Y given A is cognate to P of Y given A within our joint distribution over all the variables, if you can write it as an integral over the full conditional of Y given the treatments and the covariates, multiplied by a kernel function that satisfies the conditions up here, and then integrating out the covariate values. And then this product here, it sort of implicitly becomes our P star distribution. Okay, so that's slightly abstract. Let's have some concrete examples. So the first thing to note is that the ordinary conditional is in fact cognate to itself, because if we put in the ordinary conditional of the covariates given the outcomes, then we recover the ordinary conditional here. And similarly, the kind of classic backdoor criteria type quantity that we get from this model is also cognate to the ordinary conditional of Y given A. We just put in the margin over these covariates Z instead of its conditional on the outcome. And then we can also have slightly more complicated models. So this one, so we're sort of imagining here, maybe we've got a treatment like alcohol and an outcome like blood pressure, and then we've measured someone's genes and their socioeconomic status, but maybe we're not so interested in how their socioeconomic status modifies this effect, but we are interested in how their genes modify it. Then in this case, we could use the distribution of the socioeconomic status given the genes as our W, and then that would give us the quantity that we're interested in here. So it shows you how this distribution changes as the genetics of the person change. And we can also have slightly more exotic quantities. So here I'm going to define this Y of A as the usual potential outcome for Y when big A is set to be little a by some intervention. And we can have quantities like this one, which basically says, so what would happen to someone who had treatment A prime if we had set their treatment to be little a instead? And it's just given by this. So here we just use the W to be P of Z given A prime, and then we fix A prime over the two arms, assuming there's only two. And what's sort of nice about this, as we'll see, is that an expectation of a quantity like this appears in something called the effective treatment on the treated estimand. So it means that we can also include this as one of our contrasts in a model and also simulate from it and perform likelihood-based inference if we would like to. Okay, and then a sort of formal definition of a general Frugal parameterization is that we have these three separate parametric models. Again, we have the past, the distribution of the covariates and the treatment. We have the quantity that we're interested in modeling, and we have some dependence measure. And this distribution can be anything that's cognate to the ordinary conditional of the outcomes given the treatments and any effect modifiers. So this, as I say, means we can also model things like the effect of treatment on the treated or the effect of treatment on the controls using this parameterization very nicely. Okay, here's our main theorem, which basically says which kinds of parameterizations you can use in order to obtain a nice smooth model for P that includes some specific part P star. So essentially, it turns out you can do this if and only if the isomorphic parameterization on the ordinary conditional distribution and then the ordinary dependence measure, just now evaluated on P rather than on P star, if this parameterization is smooth, then so is this, and vice versa. So it's a very nice way to easily see whether a parameterization is a sensible one or not. So this gives us exactly what we want, the best of both worlds, a coherent joint distribution P, where we're able to specify the parametric form of this particular target of interest. Okay, any more questions at that point?
So Vanessa has done a lot of work in the Q&A, but I guess since we have an open question, we can take that one live. What copulas and possibly vines could be included in the approach?
Excellent question. Yeah, so we certainly can use vines. So I mean, what's nice about copulas is that they are pretty flexible. So you can have a wide range of margins used in them, and vine copulas are a great example of just how flexible they can be. And they mean that you can more easily put in extra conditional independences, for example, if you want to. So yeah, so there's a kind of particular sorts of independence models are available using vine copulas if you want to go that way. So yes, essentially you can use any sort of copula that works.
Robin, can I ask a short question?
Yeah.
If you go to the previous slide, so does this mean that you just need to specify? Oh,
yeah.
It doesn't mean that Y, A, and Z are all that you observe. You can kind of leave out some things, or you don't have to observe all the variables. These are just the ones that figure in this model, and that's the only parameterizations you need.
Yeah, so I mean, this is saying you're parameterizing the joint distribution of Y, A, and Z, right? And you're not parameterizing anything else. So
okay,
that's all. So anything you want to model, then you need it in your parameterization, and you need to classify it as either an outcome, a treatment, or something you want to get rid of.
okay, great, thanks.
Do you think we have time for one more question? I think
Sure.
it's related to a previous one in the Q&A. So can this approach be easily extended to a more complex situation, such as the existence of exposure mediator interactions in the outcome or categorical mediator in the outcome, etc.?
So yeah, so mediation is actually hard, and there's a sort of non-smoothness built in. So that's kind of one case we really can't do, but you can certainly do much more complicated models than this. So in particular, you can do survival models, as we'll see a bit later on. And you can also have structural nested mean models with the same approach. So you get these much more complicated time-varying structures over time. That so it's not just these little toy models that we can do. We can use this approach on.
Thank you. I think we can continue, so hopefully we can get to those models. We have time for that.
Okay, so let's do a simulation then. And our method for simulating is to first obtain data from the intervened distribution using our marginal modeling techniques, and then use rejection sampling to get back the data that comes from the observational world. So let's start off by assuming that A and B have been intervened on, and they're set now to be independent Bernoullis with parameter 1/2. And then we can sample from our copula over Y and Z, get conditional quantiles. So here I could include U in the copula if I wanted to, but I'm choosing not to. And if I did, then I could separate out the different dependencies of this sort of confounded dependence and the direct dependence. But here I'm just going to choose a Gaussian copula with a correlation that's chosen so that it's always between -1 and 1. And I choose it to depend on A in this case. I could also choose it to depend upon B if I wanted. I just haven't done that here. Okay, and then we want to make sure the margins of Z and Y have the correct distributions. So we're going to use inversion to turn Z's conditional quantiles into a conditional distribution. And we're going to choose it to have this exponential distribution with a rate given by this function here. So x of 0.2 times A minus 0.3. And then we're going to do the same thing to Y. And we're going to choose its interventional distribution to be normal with this linear mean and variance 1. And at this point, I now have samples from the intervened distribution, right? So I know exactly what form Y has, but that's not what I wanted, right? I wanted distribution from the observational distribution. So I need to do some rejection sampling. And what I'm going to do is to take the ratio of the distribution I want for B, which is this logistic regression with this probability of being equal to 1. I'm going to divide it by the probability it was actually equal to 1 in the sample, which is the same as multiplying by 2. I'll then bound that over the space of the variables and then sample some independent uniforms and reject if those uniforms are greater than the value of the ratio that results. And you can do this using our R package, which is available at this GitHub page. And you can replicate the experiments that are being demonstrated now. Okay, so we've generated now 10,000 data points from that causal model. And we're going to start just by fitting a naive regression model as though we don't know that this is not going to work. And so we're just regressing Y on A and B and hoping for the best. These are the true values that we put in. And this is the estimate that the model gives us. And you can see that the bias is several times, in the case of this intercept parameter and the B parameter, what the standard error is supposed to be. So the p-values, as you can imagine, will be very, very small. Alternatively, we could do some causal inference and actually estimate this by using inverse probability weighting. So let's fit a logistic regression for B given A and Z, because we know that this model is correctly specified. And then we can inverse weight each of the observations to get a pseudo population and fit an outcome model using those inverse weights. And this time we see that the bias is much smaller. And in fact, in every case, it's within one standard error of the true value of these parameters. So this suggests two things. First of all, our simulation is working. Excellent. And second of all, it suggests that inverse probability weighting does what it's supposed to, which is a nice side effect. But of course, because we actually have a likelihood, we can also use maximum likelihood estimation to obtain our estimates. And if we do that, we get slightly smaller bias. And indeed, the standard errors, if we compare them to the previous slide, they are again a bit smaller. And that's not surprising, of course, because we know that maximum likelihood estimation is, at least asymptotically, the most efficient method available. So just to say, this shows that if you have the correct model, then you'll get efficient estimation. But of course, it's not recommended in practice because if your model is misspecified, you may get poor estimates and be overly optimistic about your wrong estimates. Okay, so now let's form these analyses again, and this time on 1,000 different data sets, only with only 250 observations in each. And we can see that, again, the naive estimator is consistently biased. So particularly the first and third coefficients are not doing a good job of estimating the actual values. Whereas inverse probability weighting, augmented inverse probability weighting, which is doubly robust, and the maximum likely estimates are all unbiased. And it's a bit hard to see on this plot because the confounding isn't that strong, but the MLE does have slightly narrower box plots than the other two methods. And we can make the confounding a bit stronger. So before we had this function being a over 2 plus z over 2. If we change it to just z, then this exaggerates all the difficulties. So the naive method becomes even worse. Inverse probability weighting, doubly robust, and maximum likely estimation all have wider box plots now. And you can also see that the inverse probability weights are actually slightly biased at this sample size here. And similarly, doubly robust estimates are a little bit biased as well. And it's much clearer on this plot that maximum likelihood estimation is more efficient than inverse probability weighting and doubly robust estimation. Okay, excellent. So what else can we do with this method, with this parameterization? So the first thing is, and this is, I think, essentially what Vanessa was originally trying to do with the paper with Will Havercroft that I mentioned earlier, was to be able to simulate from Cox marginal structural models, which is a form of survival model where we model the probability of survival to the next time point, conditional on having survived to the previous time point, over a fixed regime of treatments. So the story is here, we have some treatments which are assumed to be assigned based on only observed variables, so i.e. this time-varying observed covariate and previous treatments. And then we're allowing, again, so this is just a direct extension of the model we had before, we allow the covariates, the time-varying covariate to be confounded with survival as well. But in terms of identification, that doesn't really make any difference. But the point is we can simulate from these models with a specified form for this marginal structural model piece. And in a sense, this resolves a sort of open problem in the literature because a lot of authors give methods for simulating from Cox marginal structural models, but they can't specify what the marginal structure is in the way that we can. So there's a nice paper by Ruth Keogh and authors where they use an additive hazard model to get data that could be from a Cox marginal structural model, and then they compute what the parameters of that Cox marginal structural model are, but they can't then so easily say, okay, I want data from this specific Cox marginal structural model. And this means that, in particular, it becomes much easier to simulate from under some null hypothesis. So maybe you think that survival is actually completely independent of the treatments. And you can also easily incorporate something like a stationarity assumption. And there's a nice paper by Jessica Young and Eric Chegan, which notes that actually this isn't at all trivial. So there's a quote from their paper talking about their own method. They say, we may therefore be limited to simulation scenarios with the proposed algorithm to unrealistic settings if we wish to simultaneously generate data under the null. And the message of this paper is you don't have to be limited to unrealistic situations. So another use which I'm particularly excited about for this method is to be able to integrate different kinds of studies into one source of evidence all about the same causal parameter. So imagine you have a treatment and a disease it's designed to treat, and you have access to a few randomized control trials as well as some large observational databases. How do we combine the evidence from those randomized control trials with the observational databases to quantitatively say how good we think this treatment is? And this is a paradigm I nickname many data. It's a sort of analogy with big data. We don't have necessarily big data sets, but we've got lots of them. And the point is, using this parameterization, we can jointly describe these models, because in the randomized control trial, the parameter of interest might just be an ordinary conditional distribution. In the observational study, it's going to be something which is some more complicated functional of the whole distribution that is generating that data. So we can jointly describe them, and indeed we are about to release a paper which uses Bayesian inference to combine a randomized control trial with a large observational database. And then the third application of this is to fitting what are called nested Markov models, some nested Markov models. And these are models which allow for generalized conditional independence constraints. And they are generalized in the sense that you have to first do an intervention, or you have to fix some variables before you'll see the independence. So it's very much inspired by the kind of causal models I've been looking at. So here is a specific example of what's known as the Verma graph. So here, the idea is that A does not have any direct effect on the outcome Y, but if you look, there's no M separation that would tell you that A is independent of Y in any sense. So if I don't condition on Z and B, then this just leaves open that path, the directed path here. But if I do condition on either Z or B, then it opens up this backdoor path here, because Z is a collider. But it turns out, perhaps unsurprisingly at this point, if you divide by the distribution of B given A and Z, then you get to a model where A now is conditionally independent of Y given B. And it's precisely because there's no directed edge from A to Y in this model that that constraint arises. So the constraint is exactly the one that we've been testing all along. So it's very easy then to fit a model and check whether that constraint is true, because we can just then compare the likelihood, for example, where this is set to have zero effect, and compare it to a model where it is not set to have zero effect. Okay, so to wrap up, we presented this Frugal parameterization and used some methods from marginal modeling to simulate from causal models. And we've also shown that we can fit these models using likelihood-based methods, specifically maximum likelihood estimation. I think the main thing I'd sort of like people to take from this talk is that a lot of causal models are marginal, and marginal models have been around for a long time, and there's a lot of things written about them. So I would suggest that looking in the marginal model literature might be a good source of inspiration for ways to attack causal problems. There are lots of other applications of these parameterizations. So we've seen marginal structural models, survival models, but you can also look at dynamic treatment regimes, structural nested models, stationarity we've mentioned briefly, and data fusion obviously is relevant to our many data paradigm. We can also do things like simulate from arbitrary instrumental variables models, which is, I think, something that just hasn't really been attempted before. So the main limitation we have is that if you've got continuous outcomes, then to simulate, you need to do this rejection sampling. And in higher dimensions, this becomes really, really inefficient. So the bound suffers from the curse of dimensionality, because for every dimension you add, you exponentially have to increase the bound. And it just means that it's very hard to get any samples at all at that kind of scale. So we've been working on Hamiltonian Monte Carlo methods to speed this up. And of course, that's great. It does come at the cost that now the data are not exactly from the distribution that you want. But that's really, there's sort of, in some sense, it seems like there's nothing we can do about that. If we can't use rejection sampling, there aren't really many other methods that give you exact samples from a distribution that you can't just evaluate directly. Okay, thank you very much.
Thanks, Robin. Super interesting. There are some questions in the Q&A, but Vanessa and Daniel are doing a good job answering. So maybe we move on to the discussion now, and then we'll have some time to chat after that about any other questions that come up. So Larry, Robin, if you can stop sharing your screen, that would be wonderful. And Larry, start.
Okay, let me get my slides up here. Hopefully everybody can see that. Is that readable?
Yes.
Yes, okay. Yeah, so I really like this work by Robin and Vanessa. When the paper first was on archive some time ago, it caught my attention because this is a problem that was brought to my attention by Jamie Robbins in the 90s, and ever since then I've kind of thought about it in the background. So this grabbed my attention. And actually, during the pandemic, I worked on some causal inference for epidemic stuff, where these epidemic models, which there's countless of them, typically have exactly this Genol problem that Robin's taught. So I was very interested. And I have to say, Robin was very kind. I annoyed him with some emails asking for some clarifications, which he kindly gave me. But well, what I thought I'd do, so if you haven't thought about this particular topic before, then I know that there's a lot of information Robin went through, and it can be kind of confusing and abstract. So I thought I would sort of give you my very quick re-explanation of what Robin and Vanessa are doing. And in particular, I have one slide where I'm going to show you kind of on one slide, here's how you would actually implement this in a very simple case, assuming I've gotten all this right. Robin and Vanessa can correct me if I'm making an error here, but so just very quickly, just to remind you what the problem is to construct a joint distribution with a given causal model. And the way I like to think about it is, if you start with a given joint distribution and I ask you, what's the causal distribution for the outcome for the counterfactual, say y of a, when I intervene and set a to be little a, that's sort of what we're more familiar with doing, and that's the G formula, right? So the way I would write that is you start with the joint distribution, you apply Robin's G formula, and you get the causal distribution. And we're kind of all used to computing causal effects that way. And what Vanessa and Robin are doing is sort of the reverse. Given a causal model, how can I construct a joint distribution that has that causal model? So I want to, you give me P of A, I'm going to construct a joint P such that that joint P, if I apply the G formula, I get back P of A. Okay, so it's kind of the reverse process in some sense. And there's lots of causal models, and in particular, Robin focused on marginal structural models. Well, he mentioned structural nested models. These were created, mainly by Jamie Robbins and his colleagues, and they're really important because for a variety of reasons, they lead to tractable estimators. They're typically semi-parametric, which means you can leave a lot of the distribution unspecified. And as Robin mentioned, they avoid this Genol paradox. In a sense, they allowed you to spend your modeling wisely. You're putting the model where it really matters. And just to give you a more complicated example of a marginal structural model, so you can see why they're so useful. Here's a typical time varying study where you have covariates, treatment, and outcome at each time over a long period of time, capital T. And if you're familiar with the G formula, you know that I can talk about the counterfactual Y if I had set all the treatments equal to particular values. And you get this complicated functional that Robin's derived. And you might say, okay, well, how do I estimate that? And as Robin pointed out, you could just stick in models wherever you see P of X given the past or Y given the past. And this is not going to work for the reasons he said, because you get this null paradox where, strangely enough, you're going to end up rejecting the null hypothesis even when there's no treatment effect. So if you haven't seen that before, you can trust us that that's the case. But a marginal structure model can really simplify things. So you might say, well, I think the treatment effect could be approximated by a linear function like this. And then you can estimate the treatment effect very easily. We just use an estimating equation to estimate the betas, and you get no null paradox, and you haven't even had to specify the whole data generating process. So that's just to remind you why things like marginal structural models are so important and so useful. But as was pointed out, they only specify a part of the distribution. So why do you want to specify the rest of the distribution? Robin already told you for simulation, convenience of parametric models, and so on. He didn't mention checking fit. I wonder, it's going to something I'll ask about at the end, is I think maybe these methods could be used once you have the rest of the model specified. If you do that flexibly, then the only thing in question is the marginal structural model. And so we could look at residuals and things like that and perhaps check fit. So I'm going to give you my one slide summary of how to do this. But first, just to remind you of the notation, P sub A or P Y set A or do A, as Pearl likes to say it, or with the counterfactor, they all mean the same thing here in what I'm in these slides. That's just the causal distribution of Y when you set A, which is given by this G formula. And the other thing Robin mentioned, just to remind you, is these things called copulas. The key thing here is any joint density can always be written as its marginals times this extra thing called the copula density. Okay, so that's just to remind you of some of the notation that came up. So this is my one slide summary of how you do this, and I hope I've got it right. This is the basic frugal construction in a toy model. And as Robin emphasized, you can do this in complicated models too. But so here's the idea. I have covariates or confounders X, treatment A, outcome Y. I want to specify some joint distribution. So step one is I'm going to write this as the past, P of X, Y, and then the density of Y given the past. So I haven't done anything yet. Now, I'm going to use the fact that the density of Y given X and A is exactly the same as the causal distribution of Y given X set A. And that's why don't I have to do a G formula or something like that? That's because we've also conditioning on all of the covariates in this problem. So this is a particular case where conditioning and finding the causal distribution just happen to be the same, not true in general, but just in this simple case. So I haven't done anything except to rewrite things this way. And now I look at this and I say, well, think of A as fixed. And now I just have a density for Y given X. So I'm just going to use the definition of conditional density and write that as the joint divided by the marginal. So again, I have just elementary probability. Next step is I'm going to use this copula idea. I take this is a joint density, so I can always write it as its the marginals, X and marginal for Y, times some copula. And you can see this part's going to cancel, the PAX is going to cancel. This first part is just whatever density you're specifying for X and A, and the things in the red and the blue, the red is something we've already pre-specified. This is what I wanted to inject into the model. This is my marginal structural model. This is the density for Y when A is fixed. And so we're starting with the assumption that I've specified a model for this. And this is somehow the whole game is I want to construct a joint density for everything and inject this into the model somehow. And Vanessa's construction allows me to do it here because now I can just stick it in here, but I've just got to specify one extra piece, say this copula. And so we're done. Is what this is saying is I can rewrite the joint density as the density of X and A. I can put in anything I want there. I put in my marginal structural model here, which I have control over now, and then I have to just specify some sort of copula. And so this is, as I understand it, if I've done it right, how I would use the frugal parameterization to inject a marginal structural model and get out a well-specified joint density. Now, of course, in more complicated situations, it's not that simple, but this is the basic idea. And really, I should have put parameters and everything. And the nice thing is that I can take these to be variation independent. That is, I can freely vary beta and gamma and alpha, and that's important. And if you're interested just in the conditional distribution of Y given XA, by the way, that just now becomes the marginal structural model times this copula. And I just want to emphasize this variation independence is important. It's one of the ingredients in the null paradox. I will say that I'm not convinced that completely solves the null paradox. I'll come back to this point. If the model's correct, the variation independence does solve the null paradox. You won't end up rejecting the null incorrectly. But if the model is just an approximation, as it always is, there can still, I think, be, you're not guaranteed necessarily to get the parameter beta be zero because you're estimating a projection. So there might be some, you might say residual null paradox, but in some sense it's reduced. All right, so now I'm just going to get to conclude with a few questions. There are other attempts to do this. There's one by Babino, Andrea Ratnitsky, and Jamie Robbins, which it's the paper's written in terms of regression functions, but you can do the same thing in terms of densities. And I think it would go like this. You would define this ratio, which is simply the density of y given x and a divided by the same thing at some baseline value of x. I'm just picking 0. It doesn't have to be that. And then you can check that the density of y given x and a can actually be written now as there's our marginal structure model. There's this ratio, and this is just sort of like a normalizing constant. Now, this here to me looks just fairly simple. I will say when there's multiple time points, I think the Frugal parameterization is easier and more interpretable, because I think copulas are sort of, you know, we can construct things like Vine copulas and things like that for many time points. This becomes now a nested kind of iterative construction, which is a little bit more hard to understand, I think. But still, I'm just curious how it might compare to this parameterization. Is this feasible in a time-varying study with many time points? Is the next question. And in principle, it is, because again, all you need now is sort of a bigger copula. This was very interesting to me, because again, I was working on some epidemic models where we had many, many time points, and I was trying to imagine how I would repair those models in the sense of trying to do some modify the model using a Frugal parameterization. So I think it is feasible, and in fact, in the paper, of course, you guys talk about that. But you are now having to specify a bigger and bigger model and you know, more complicated copula. So maybe you could just make some comments about how practical that is. And the other thing is, yeah, this is a question. So let's look at this P of x, a, y. Again, I can specify, so here's the Frugal parameterization. So I can take P of x, I can make this to be something very flexible, even non-parametric. I can take my copula to be a very flexible model, maybe even a non-parametric thing, and then put in my marginal structural model. What have I constructed then? Well, I've constructed essentially a semi-parametric model. Basically, it's fully non-parametric except for the marginal structural model, but the rest of it's all kind of almost unconstrained. And I'm wondering if doing that might be useful as a way of doing model checking, because now I can like simulate from this, figure out what the residual should look like. And if I see any measure of misfit, since all of this is very flexible, the only thing I can blame is the marginal structural model. So I don't know if that's practical or not, but that's my question is, do you think I can use the Frugal parameterization then as a way of doing model checking for things like marginal structural models, which might not be so easy in like time varying settings and so on. And this other question, more technical one, which is, if the model's correct, I'm convinced the Frugal parameterization actually solves the null paradox. If the model's wrong, I can still fit a marginal structural model using like estimating equations, for example, without specifying a model. And hopefully, under some conditions, of course, we can still avoid the null paradox, although you have to specify, say, propensity scores and things like that. But if I just use the Frugal parameterization and fit that model, I'm fitting this projection, and I have the benefit of the variation independence. But I'm just wondering, is it still true that I'm going to avoid the null paradox, or could there be still some null paradox due to model misspecification? By the way, one other thing I wanted to mention, which I forgot to put in my slides, is you'll notice in Robin's slides, there's this variable u that appears all over the place. And if you want to read more about this stuff, that u is very important. I call those things phantoms because they're unobserved, but they're not confounders. And they play an important role in all this stuff. So I just want to mention that if you're interested in this stuff, keep your eyes open for those phantoms, because they're actually, they cause a lot of the problems that Robin's talking about. Okay, that's the end of my discussion. Very nice. I think it's really great work that Vanessa and Robin have done, and congratulations on a really nice paper.
Thank you.
Thank you, Larry, for a nice discussion. Okay, so Robin, Vanessa, I guess Daniel as well, if you want to kind of answer some questions, now would be the time.
Yeah, so I hadn't actually seen this Babino paper before, but it looks to me like that's just another way that you could specify your dependent structure, right, by using that ratio instead of the copula. So yes, I guess this is something we should investigate. But yeah, I mean, if it's computationally feasible, that would be excellent. You mind just sharing your slides again so that people can see the questions?
Oh, yeah, let's see.
Thanks. So then the second question, yes, it is feasible in a time-varying study with many time points. So obviously you have to specify more models, that's true. But I think that's sort of inevitable, whatever method you're using, right? Somehow those models need to be specified if you want it to be realistic, right? So I can't sort of think of any other way that would be simpler and yet give you the flexibility that this parameterization does. Computationally, we've said that the simulation gets harder with many time points, and then obviously we have to we're sort of reduced to then using something like a Monte Carlo method to get samples from it, and we're relatively early stages with that, but it seemed as though that's working well. So I'm optimistic that will be the way that we do things in the future. Can we check the fit? Yes, I mean, so obviously I mentioned the Verma model and said you could use a likelihood ratio test, for example, but as you say, you don't have to use a likelihood ratio test. And you're right, you could easily simulate from some data from it and maybe compare the residuals to the ones you get in your actual data set and see whether they look plausible, and whatever other kinds of tests you might want to do. And then for 4, obviously, no, I mean, I wouldn't really call it a paradox in this case. It's just you've got the wrong model. So the hypothesis may reject incorrectly. I would presume that one can use similar techniques to the methods used in estimating equations to try and alleviate that. But as you say, presumably it will involve specifying something else correctly, like the propensity score, in order to guarantee that. Yeah, do you have anything you want to add, Vanessa?
No, but they are all excellent points and things we should follow up, and especially also the model fitting of the marginal structure model. And also maybe one point to add is the use in sensitivity analysis, which is also in response to one of the questions in the Q&A. So we think that an application would also be in doing some sensitivity analysis with latent confounding.
Great, thank you all. So we are a little bit over time, which is a shame because so it's such a nice discussion too. So maybe then we wrap up. Larry, you can stop sharing your screen now. Thank you so much. Sorry, lost myself. Okay. All right. So I'd like to thank once more Larry, Robin, Vanessa, and Daniel for giving such nice talks and answering so many questions. If your question hasn't been answered and you've asked it in the Q&A, just know that we will pass on all the questions to the speakers after the talk. So if you want to get in touch with them to further discuss, that's totally possible. Next week, we have an interview with Philip David from University of Cambridge. So hopefully you will all join us for that. We'll actually have Vanessa back on here as a special guest for that interview. Yeah, so hope to see you all then.